Assalamualaikum warahmatullahi wabarakatuh. I am Brother Shahrin representing my group, which is group 1, on our case study on the Korsmeyer Peppas model for Metformin extended release tablets using on HPMC hydrophilic matrix systems. In this case, the solution studies were conducted and the release data were fitted to the Korsmeyer Peppas model. The release exponent n obtained was 0.92 for a cylindrical tablets. So what is the problems? This value indicates a specific release mechanisms that may not be an optimal for extended release metformin formulation. The Korsmeyer Peppas power law model is written as mt over m infinity equals to the k times to the t to the power of n. So mt over m infinity is the fractions of the drug released by the time t, mt is the cumulative mass released at time t, and m infinity is the total mass released at the infinite times, essentially the total dose. So the constant k incorporates structural and the geometric characteristics of the matrix, while the n is the diffusional exponents that provides insights into the release mechanisms. For cylindrical matrix, the interpretations follows known thresholds. Fickin or case 1 diffusions give n approximately 0.45. Anomalous non-Fickin transport falls between 0.45 and 0.89. Case 2 transport is approximately 0.89, indicating a polymer realization limited release. Our observed n letter equals to the 0.92 lies above the case 2 criterions, indicating a super case 2 transport. So this means that the drug release is governed mainly by the polymer realizations, swellings, and erosions rather than the simple diffusion alone. There are two key formulation factors that leads to this high N value. So first, high viscosity HPMC grades or high polymer concentration produces a very strong thick gel layer that hydrates slowly, emphasizing polymerizations and erosions. Second, metformin is highly water-soluble drugs. So when the drug dissolves quickly, the release rates becomes limited by how fast the polymer relaxes or erodes, so pushing the N letter upwards towards the super case 2 transports. So as for the formulation strategy, our first strategy is to use high viscosity HPMC K100M combined with the hydroxypropyl cellulose or HPC. High viscosity HPMC provides good tensile strength but risk of payoff, so the HPC is added to improve the film adhesions. So the combinations of the HPC and the HPMC K100M forms a cohesive gel barrier that dissolves slowly, increasing the HPMC K100M proportion while reducing the HPC content strengthens the gel barrier, decrease the matrix erosions, and shift the release mechanisms towards anomalous or frequent diffusions rather than the super case 2 transports. Our second strategy is to incorporate the hydrophobic retardants such as ethylcellulose. Ethylcellulose is a hydrophobic in nature, so it retards diffusions of the dissolution mediums into the matrix. As the ethylcellulose concentration increases, the drug release rate decreases significantly. Formulations combining the HPMC with the ethylcellulose shows the N values ranging from 0.45 to 0.89, which indicating a coupled diffusions and realizations or anomalous transports. The hydrophobic polymers stabilize the matrix and prevent rapid expansions of the gel networks, providing a more sustained and predictable drug release kinetics. Controlling the release mechanism is important because it ensures predictable drug absorptions and maintains stable therapeutic effects. So in conclusion, so N equals to the 0.92 indicates a super case 2 transports dominated by the polymer realizations. So by using HPMC K100M with the HPC and incorporating hydrophobic retardants like ethylcellulose, we can shift the mechanisms towards anomalous transports for better controlled release. So that is all the case study for our groups. Thanks for watching.